stuck on. Let's go over them now. Okay, it's working. You said 12, Jesse?
Yes.
So 12 is asking us to just find the equation of a tangent line. So we think about, what is a tangent line? It's a line. What do lines have? Lines have a slope and they have a point. They have infinitely many points, but to write the equation of a line, you need a point and you need a slope. So for this one, first we're going to sketch it. So sketching it's pretty straightforward. Here's the point 9,3. Okay, that's a pretty good sketch, I guess. There's my tangent line. And so I go, okay, my line has the point 9,3, which makes sense because the graph, it's f of x equals square root of x. So if you plug in 9, you get 3, right? And then now I need to, so I'm basically just one piece of information away from the equation, right? I just get the slope. So to get the slope, you take the derivative. My derivative would be 1 over 2 root x. Everyone okay with that? Now, that's a general formula for getting the derivative at any point on this line, right? Now, so what do I plug in here? Do I want to plug in the 9 or the 3? The 9. So let's plug in the 9. So if I read this, if I read it literally, it says f prime of 9. It's just literally reading the symbols. But if I read what it means, it says this means what is the slope of the tangent line of this function when x is 9? And so if I plug that in, so 1 over 2 root 9, so that's 1 over 2 times 3. So 1/6. Now we ask ourselves, does that agree with our just kind of common sense? Like if I got an answer like -5, I'd be like, I'd say, that doesn't make sense. But I am expecting some kind of positive, not very big number, which 1/6 is that. And so now I got to use point slope form. So remember the way point slope form works is like this. I'm using M to describe. By the way, these are always fun. Let's be super duper technical. There's not really a need for this, but you could say. It's good to see if you can understand this notation. This is totally like AP style, if you're wondering. It's like on a multiple choice, I'm going to ask you. There'll be many choices of that form, but do you guys see what this is saying?
Yeah.
It's like 9 is my x value. Because the question might be something like, which of these describes? They probably wouldn't even give you like a formula. They would just say, which of these equations describes the tangent line equation at the x value of 9 for some general function? And this is it, because there's x minus x1, there's y minus y1s, because f of 9 is just the y value of the function. Yeah. And then f prime of 9 is the slope at that x value. So anyway, for our problem here, it would just be y minus 3 equals, the slope was 1/6. And then, there we go, we're done. Cool beans? So yeah, point slope form is definitely one that is useful to know when you're studying this kind of stuff, because so often when you're studying calculus, you have a point and you have a slope. So point slope form. What was the other one? You want to look at?
16. I just like, what do you want from the explaining of the values?
Oh, just a statement like, let me give you a quick example here. So, yeah, off the top of my head, I guess might not be the best, but say you lived in this purely utopian capitalist society where the price of ice cream was like highly variable. Here's the price of ice cream. I'll call this P. And here was like, say, the temperature. So as the temperature increased, the price of ice cream would increase because they just price gouge you. And then what you could talk, oh, let's make it more interesting. Let's say it's some kind of concave, some kind of curve where it's, oh man, as you push into the 80s and 90s, it really starts to ramp up. You know, go to Sweet Peaks and they're like, that'll be $14 for a single scoop. Kind of thing. What you could talk about is, what is the derivative, right? The change in price with respect to the change in temperature. You can talk about that. But let's say also, you could also, say there was some other way of, I don't know, how does the price depend on, I don't know, cow population? Who knows? I don't know. This is a terrible example, but you could also talk about the change in the price with respect to how many cows there are. Maybe this would be some kind of inverted curve because the more cows there are, the more ice cream you can make. But you get what I'm talking about at all? I'm talking about you can take the derivative of a quantity with respect to some other quantity. So with this one, you've got volume and side length. So that thing's been making all sorts of weird noises. So when you have V equals S cubed, right? This is a pretty familiar formula, hopefully. Here's a cube, here's a side length S, S by S by S. And you can say, okay, the change in the volume with respect to the side length is 3 times S squared. Does that make sense? But then that derivative evaluated when the side length is 4. So can you guys, in your head, picture a growing cube?
Yeah.
Imagine a cube was expanding. Does it make intuitive sense to you why, if the cube was small, it wouldn't be growing that fast in terms of like volume? I can give you a really concrete example if that's confusing. I'll just make a little table of values here. So here's side length and, okay, so let's say the cube was 1 by 1 by 1, volume's 1. 2 by 2 by 2, you get 8. 3 by 3 by 3, you get 27. 4 by 4 by 4, you get 64. Well, you can see the bigger the cube is, adding 1 to the side length, right, increase this by, 37. Whereas increasing 1 here only increase it by 19. So then when you evaluate at 4, you can see you plug in the 4. 3 times 4 squared is 48. All right, is this making sense? Now the units can get really weird here. What do you think the units are of a change in volume with respect to a change in side length? Let's say it was feet. I don't know. Let's say it was all feet. What was my change in volume? What kind of units? Cubic feet. What were my units of side length? Just feet. Kind of a weird one, right? You would be talking about how many cubic feet of volume growth are you getting per foot of side length growth at this particular moment in time. We understand that?
Yeah.
So as far as making it into a sentence, it's like, okay, are we talking about cubic feet per second? No, we're talking about cubic feet per feet. Or if it was inches, cubic inches per inch, or if it was centimeters, cubic centimeters per centimeter. Way to think about that, like that's what's cubic feet per feet is square feet. So there's a connection between the volume change with respect to length and surface area. As you've seen, if you finish 17, the derivative of the volume function is actually the surface area function. Does that make any sense? No? Lots of blank stares, that's good. That's a good sign. So I talked the other day about why that is. Why is the derivative of the volume the surface area? But it's not true in this case. Right. What's the surface area of a cube? Six times s squared. So this is only half as big. That's kind of weird. And the reason for that is, what you guys can say. Why is it that the derivative of, so quick recap, the derivative of here's a circle. The area is pi r squared. The derivative of the area with respect to its radius is 2 pi r. Ah, interesting. Derivative of the area got us circumference, and that's because if you expand, if you do a little change in r, then this is the extra area I gain by expanding the circle. This is the change in area. And if you think about this area, right, the area, the small change in area would in fact be this length, 2 pi r, times the thickness, dr. And that gets us that. Now you can expand that argument out to a sphere. What? Confused?
Okay, so my question is like, why would the dr like so I get where the area comes from, but why'd you draw like that second circle like around it, like to get your dr? Like where's that come from? That's like the.
What's so funny?
I am confused.
Yeah, that's fine. Well, when we talked about this last week, I mean, did this not make sense last week?
Yeah.
Okay. So real quick, this is a pretty, I mean, it's pretty important understanding, I think. Here, I'll just go slower here. Ready? So here's a circle. Okay. The radius is r. Right.
Yes.
We all agree that by definition, the circumference is 2 pi r. When I say by definition, I mean literally that's what pi is. Like if you think way back in like in elementary school or middle school, you might have taken some string and you put it around a circle and you go, huh? You measure the string and you say, oh, the distance around the circle is always like 3.14 times bigger than the diameter of the circle, right? And you go, okay, we're going to call that number pi. That number is pi, okay? That's literally what it is, okay? So that's just true by definition. All right, and then you say, all right, what happens if we, and of course you can derive using, in geometry, you usually break this up into a bunch of triangles, and you can show why the area is pi r squared. Okay, you basically split it up into you slice it into like a bunch of little triangles, and then you expand them out, and you show that this is true. Okay, so then you say, well, now I want to know about what's happening as you expand the circle. So what happens if you take a circle and grow it? All right, so you ready to grow it?
Yes.
So stop me if I get to the point that's confusing anyone. So if you're like, that step doesn't make sense, let me know. So let's add on a little bit of radius. How do I denote that? How do I write a small amount of radius being added on? Well, dr. Does everyone understand that? Dr means a tiny little change in radius. Now I had to draw mine to be like, I mean, that's like an inch, but in real life, it's infinitesimally small, okay? Now what I've done, I just expanded the radius a little bit, right? So this is my new circle. Are we cool with that? So this is my original area, and I'm gonna shade in this, that was a little tiny change in area, right? So hopefully you'd agree that this was my original area, and this extra area that I've gained by expanding the circle is called the small change in area. Cool beans? All right, so now, pretend for a moment that I can cut this and then unwrap it. I'm gonna unwrap this little thing. Now keep in mind, it's infinitesimally thin, so I can think about it like a rectangle. It's a very thin band. How thick is the band? dr, and then how long is the band? No, 2 pi r, because 2 pi r is this distance around. So that's the width. So I'm taking this band and I'm peeling it right out. Now the area of the band is dA. That's that area that I just created. So now what's the relationship here? Now I go back to basics and say, well, it's a rectangle, really thin rectangle. So I can say that 2 pi r times dr is equal to dA. Move that dude down there. And now we have, now if you're thinking, well, wait a second, all I did was I used my calculus rules and I went like this. Yeah, that's all you had to do. What I just showed you here. So if you're confused right now, like, wait, you just made that really complicated to find the derivative. This is explaining why, the big capital W, why does this result? Is this just a weird kind of like coincidence, or is this something fundamental going on? And it's the latter. This is something fundamental about derivatives on how they relate to like spaces. So I don't know. Does that clear things up at all?
Yes.
So now take your mind and imagine a sphere. This is gonna be hard for me to draw. I think the drawing looks make it. It's like glass.
No.
Well, that was paper.
Oh. Picture a sphere. It's fine. It's probably fine. Picture a sphere. Now imagine. Now that sphere has volume, right? Now imagine expanding that sphere ever so slightly. That would create a small film, so to speak, like a little layer around the sphere. That would be called dV. So it's this sphere problem. I should erase that. Oh well. Okay, so imagine this. I'll try to draw it, I guess. I'll go back when I said, here's a sphere. Now imagine expanding that radius out a little bit. Oh God, this is tough. Okay, so you've expanded the sphere out by some amount dr. Well, what's the surface area of a sphere? Well, it's 4 pi r squared. And then how thick is that? So that's the surface area of this film that I've created, this layer. And I multiply it by the thickness, dr, and that would tell me the change in volume. That's the extra volume I got on that sphere. Again, rearrange the formula, and you get this famous result, which is that the derivative of a sphere's volume function with respect to its radius is the surface area formula for a sphere. Does that make sense?
Yes.
Okay, okay.
Wait, because you did the surface area at the beginning.
Yeah, so what I showed was, wait.
Wait, did you mean the volume?
I may have misspoken, so sorry. So I started the sphere, that sphere had a volume, and I went, boop. I expanded the radius ever so slightly. So basically I added like a layer of silly putty onto this. And that silly putty has now this is where I can't really draw it. You have to imagine unraveling that and saying that that silly putty has this much area and it's this thick. So the volume of that silly putty is this. And then we get the result. Now again, in practice, watch how easy it is. Hey, here's a formula. What's the derivative? Takes 2 seconds, right? So in practice, if you have a formula, taking the derivative is very easy, right? But in certain contexts, if you really want to understand what's going on, like under the hood, so to speak, it requires, this is kind of hard to visualize, I think. I mean, it's not easy. This one's a little bit easier because you can draw it without too much trouble. Okay, thoroughly confused? Yes, Caleb.
So when you were using the example of the string around the circle,
Yeah.
to like find the thing, wouldn't that technically be string theory?
Next on this class.
Okay. Now here's this. Hopefully, will bring things full circle here, because you might be going, okay, I guess I get what you're saying there, but then why does this fall apart on a cube? A cube is a pretty simple shape. So why does this fall apart? Well, it does and it doesn't. So I'm going to try my best to be a good artist for you. Ready? So here's a cube. Okay. But there's a thing, so here's S, here's S, here is S. Now, when we expand S, watch what happens. I swear I'm trying my best here. This will require some serious, actually, you know what I'm going to do? It's just so hard to draw. But, okay, I'll keep going. I'll try to draw it. I'll try my best. I've just expanded the cube. So in 3 dimensions. So, but think of this point as being fixed in space. So when I expand the cube out, so when I expand the cube out, only, it's not true that every single, we don't get a full uniform layer around the cube. Only 1, 2, 3 faces actually got that thickness added on. Okay, this one probably would require some pretty deep thought to visualize it. I can't really get it into your brain directly, but you just have to. What you do a lot of times in practice is you just do the calculate. There's a famous saying when you study, if you ever study quantum mechanics, like in physics, they say shut up and calculate, which is a way of saying like sometimes stuff gets really complicated. So you start with the calculation and then you try to understand it. So like in this case, you say my volume is s cubed, and then you say, okay, so the change in volume with respect to the side length is 3s squared. So it's not, so that tells me it's not that simple connection like with a sphere. And it has to do with, like, again, if I add in this little ds, I'm not getting all, on a sphere, the entire thing was expanding out uniformly when I changed r. But in this case, the way I'm drawing this, it's only the right top and back face that are getting those little slabs added on. So that would be 3 times s squared. Okay, so anyway, for 16, all you want to say is, yeah, the volume. So at the moment when the side length is 4, assuming the cube is expanding, the volume is changing at a rate of 48 cubic units per unit with respect to the side length. Okay? All right, are we feeling okay? How are we doing with the piecewise functions? Are there any more questions?
Is there a way to calculate like splitting the ds to like each end of the extension, like instead of putting it on?
Guys, hold on, I cannot hear what she's
This
saying.
isn't really like important for this specific class, but well, I guess this question, but like, can you split the ds in half and put it on one end and then the other end
Yes.
to make it a film?
Yes, because then you'd have 1/2 ds s squared on each one. So then you'd have 6. Yeah, exactly. You're totally correct. So you have all 6 faces. It'd be having little slabs on them, but you'd have 6 times 1/2 s squared ds is the change in volume, and then again you get a 3 there. So very good point to make. She was asking, could you distribute that ds halfway across and center the cube in the middle of your expansion? And the answer is yeah, but you'd still end up. You got to do it very carefully though. Sometimes people will try to do that. And they'll add effectively 2 ds's, and then they'll get turned around in their head because they're like, well, now I do have 6s squared, which is not what the answer should be.
Are we gonna have a quiz on Wednesday for this? That's right, well, TSA.
I was thinking either tomorrow or Wednesday. Yeah, I mean. No, this one will be in class.
Well, then it's not really